analog world, and indeed the cable was at fault. So hopefully the recording on this one will go okay. Okay, so last time within this class I started a topic that will continue through all of today and quite possibly will leak some into next session. And that has to do with this issue of strictness and laziness as a particular example of non-strictness. So again, what does it mean for a function to be non-strict? Anyone? We have a function that's non-strict. What's the implication of that? So we had up here some indication of a function taking some argument, and if we say that function is non-strict, then what would that indicate?
That is lazy.
Sorry?
That is lazy.
Okay, laziness, it turns out, is a particular type of non-strictness. So it often goes together, but I'll accept that as a general answer, that it's one way to be non-strict is to be lazy. And what would laziness mean, for example, here?
It would compute at runtime. So.
Okay, compute what?
The conditions.
Okay. So there's a very particular thing that computation would involve, or that condition. It would involve X, right? So the idea here, if it were lazy, is it wouldn't actually compute X until it needs it. And that's one way that you can achieve non-strictness. But in general, non-strictness means that we could give this function a non-terminating computation, or in fact, as an argument, a computation that involves an error. And it needn't be the case that yields the function to not terminate, or the function to cause an error. So we could give it this value that's problematic in some sense. It doesn't finish, and we might have a situation where the function itself does finish. We give it a value that to compute it would take forever. It wouldn't halt. And yet the function itself would halt. Function would return a value. Maybe it would return a random number. Half the time it returns a number, half the time it returns whatever X is. But in any case, it's possible that it won't halt. So this is an example. This relates to the notion of non-strictness in general. And laziness is one particular way of realizing non-strictness that's very useful. The idea being we don't actually compute the argument. We don't actually evaluate it unless, in fact, we need it. And in some cases, we may not need it. Okay, so there's two types of laziness that are supported in this programming language, Scala, that we're examining here. And one of the reasons I like Scala is it does support both types. One is a notion of laziness by need. Here it waits until it needs it to compute it. It computes it, and then it memoizes the value. We could say informally that it caches the value. What do I mean by that? Anyone?
The next time it's needed, it's not computed.
Exactly, it's not computed again. It's done the job, it's computed it. Now that it has computed it, it'll just use that value on an ongoing basis. So it just waits to figure out, is this really needed before doing the work? And once the work is done, it uses that value. And we're going to see, as a central part of today's lecture, how streams support that sort of type of memoization. Okay, we're going to see how streams, in particular, allow us to go and and have a whole series of computations. And when one is computed, that information is memoized, it's remembered, so that if we refer to that particular element again, we can remember what the value is and use it directly. But until that value is actually accessed, it's not computed. Okay? Here, we compute it by need, and once we've got it, we use that value on an ongoing basis. The other type of laziness, which you'll see in some languages, and which you'll see in Java and Scala additionally, is something called by name laziness. And here, the idea is each time a value is required, it's recomputed. So each time we see a reference to this parameter, let's imagine that internally it refers to it as x as well. Each time we see that reference, it recomputes it. So there, x kind of stands for a computation. It stands for an expression of a computation. It stands for what is to be computed. And each time we refer to it, we recompute that. Okay? And as we'll see, this is very similar to what we did last time with no parameter lambdas, with no parameter anonymous functions. Every time we evaluate it, we get it as well. And we actually saw that in Scala last time with this syntax here. It's called by name. So here we give it an expression, and that expression gets reevaluated. Okay, and it turns out that this by name type of situation, type of context, does not cache the value. It does no, because each time it's referred to, it recomputes it. And it turns out that we can get that very easily in Scala on an arbitrary collection by calling .view. Okay, with it. Okay, so I'm going to go through 4 mechanisms in Scala that support this type of these types of alternatives by need and by name types of use of laziness. Okay, the first 2 we're going to go through quickly, mainly because we started the first one before, and the second one is pretty straightforward to understand. We're going to spend most of our time today on streams and possibly some next time as well, because they are extremely powerful and they are conceptually very, very important to understand, particularly when we think about use of laziness and use of, in fact, Scala as a programming language in the context of modern high-performance data science tools like Apache Spark. Okay, with the Spark project making central use of Scala and of laziness for some reasons we'll be seeing with streams. Okay, so by name parameters. We saw this last time, and I just want to reinforce this here. So I'm going to introduce it a slightly different way, but it's going to get us back to material we covered in last class in important ways in the latter part of it. So the first point here is we're going to define a function called print and return n. Okay, and I'm just doing this to give you a very concrete sense of how many times things are being evaluated, when they're being evaluated. And specifically, this is going to be a function. It's kind of an identity function. It takes in a number, and it returns that same number. This is how we say return. The last, ladies and gentlemen, in Scala, everything is an expression. Everything is a formula. And the last, if you have a sequence of them, the last one is the one that's used as the value for the whole block. So here, n is the value for the whole block. So this is a function that takes in n and it returns n. But it does something along the way. It has a side effect. And what is that side effect? Prints something. Yeah, it prints out the value. Okay. So, well, I mean, let's do it, right? Let's do it together here. And oh, I was having fun this morning. Okay. But I'm actually going to go to a place where, okay, I have the document that I sent you earlier, because we're going to use that as well, document. So I'm going to start up the Scala shell there so I can just refer to it right here. Okay, so let's go and let's define this. Print and return n, right? Here we go. Def print and return return n. Probably it should say print identity or something like that, but I was uncreative. Okay, and this will print ln of n, and it will return n there. Semicolons in Scala are used, ladies and gentlemen, when things are on the same line to indicate separation. You don't need semicolons in general unless things are on the same line. Okay, so Scala is the language which puts a premium, a little bit like Python, on succinct, terse syntax to allow you to express rich computations with a minimal of mechanism, with a minimum of fuss and muss. Okay, and here we see I can just refer to n. I don't need a semicolon after it. After all, the C-like languages have led to sort of a cancer of the semicolon, which is pretty unpleasant. Okay, so here we have print and return n. Okay, so what if we call this print and return n? What if we call it with 1? What do we see? This is not a trick question. It'll print 1 and it'll return 1. And if we do it with 3, it'll print 1 and return 3. Okay, great. You may ask, okay, why am I doing that? Well, I'm doing that because I want to examine the implications of calling. So let's do this eager printf. Do I need to do that? What's going to happen if I do this? Sure, let's do this. This is not named after Derek Eager. This is eager printfn is just like a standard function with the standard calling conventions that you have learned to love. Eager printfn, and I'll leave out the 4. I was fooling around with different variants of things, and here we go. We could just use equal. We don't need this curly bracket. This is for a block. If we have a series of things, we don't need it, and so here it's just this value. Yeah. So if I call eager printfn on and give it as an argument 3, what is it going to give me? Thank you. Okay. Must have been was it a niter? Okay, so here we go. And how do I do this? What is it going to give me?
1.
It's going to give me 2. And it's going to print out 1. Where's this 1 coming from?
Print.
Yeah, it's coming from the print inside of it. So if I do 3 here, it's going to print out this. Because remember, in the definition of print and return. Sorry? Oh, is it?
Yeah, there's chopping out the very first digit in the string.
Oh, okay. Okay, there. Can you see it? It's peeking out now. Okay. Let me frob this and. Okay. Anyway. Okay. So this 3 resulted from what? This 3 resulted from the print inside here, right? Gosh, maybe just to make this even more clear, so you don't have to guess which one came from where. I'm gonna actually modify this. Okay, now it's off the bottom. Okay, life is challenging. Okay, there we go. I'm going to slightly redefine this to say print, number 1, this. Okay. So this is occurring at this point. So now every time I call this, it's going to say pound. The number is 3. Okay. So we know this part of it came from here, right? And this part of it was the value resulting from eager printfn, which simply took whatever this gave and added it to itself. So why are we only seeing, so what's going on here? When is this thing being printed out? At a mechanical level, when is this thing being printed? At what point in the evaluation?
When 3 gets placed between the brackets.
Yeah, okay, so what's happening here is that eager printfn expects what as an integer? Remember? Eager printfn expects a value as an integer, right? When is this value being evaluated to 3, and when is this being printed? It's being printed right here. Before the call is made, the value being passed needs to be determined, right? Before this call, before we call eager printfn, this thing being highlighted right now is evaluated. And we get back a number, right? And then that number is given to eager printfn as the value of its n, right? It's given, or v. It's given as the value is v, right? And it takes that number, that particular number, and adds it to itself. True or not? Okay, thank you. So, ladies and gentlemen, conceptually simple. We evaluated v before we call it, and then we evaluate the body of eager printfn with v. Hope you feel very familiar with that, because that's the paradigm you've been operating in for years. And if you don't, please come to office hours. Okay. Now, last time we created something like this, deferred printfn, and here we took in a what? A function or a closure. Yeah. Technically, it's a closure. It's a function with an environment in which its values are bound in which it's the names used in it are bound to values. Okay, so this is actually a closure passed in, but we can informally call it a function. Okay, it's a function that knows how to value itself. It knows the values of all the names in it. And here we're going to set this to be this thing here. So we take in this function called fn_get_v, and then we are going to add a call to that to a call to that. What is that going to give us? So if we give this, if we create this and we pass it this, what is that going to return?
4 twice and then 8.
Okay, good. So why 4 twice? Why is it going to print out 4 twice?
Because you're calling it twice.
Because we are in fact calling this function twice, and that evaluates this, and so it's calling print to return n on 4 twice. Do you appreciate that? This is a function. It's a closure. And which closure are we giving it? We're giving it this one. The one that takes nothing as an argument, and it calls print to return n of 4. And we are calling it once, getting a number. We're calling it twice and getting that number. And each time we call that, it's evaluating the body of this function, which then goes and calls print to return n. So we're going to see 4 printed twice. Do people appreciate that? I'm not saying appreciate that you like it, but do grok it? Do you understand it? Grok or not? Good. Okay. Okay. So we could type that in, and I would say sure. What the heck? Def print. Okay, it's called deferred printfn, not eager, but deferred. Deferred printfn. Okay. And here we go. We'll get fn get v, and there we go. And we'll do fn get v. Here we are. There we are. Okay. So this takes in a function, takes in a closure, and that closure tells it what to do when we want to get the value. We just have to call it because it's a function, it's a closure. We have to call it to get back the value. We'll call it twice. So it will perform its job twice, and its job will be to call this print and return n, right? Deferred print fn, okay? And we are going to give it a function. Why are we giving it a function? Because it needs a function to do its job. It needs a closure. And this is going to be print and return n of 4. And we called it, and lo and behold, it's doing it twice. Why twice? One for this time when this is being called and evaluated, one for that time. Grok or not? Grok. Okay, good. Okay, so it's being evaluated twice. And ladies and gentlemen, that is what is going on secretly for the next one, which is called by name. This guy here. So we're going to have this call by name, okay? And instead of having all that extra syntactic sort of cruft, we'll just do it this way. Here we get in a recipe. We get in a recipe for how to compute an int. And we'll then take that recipe, add one to the other, okay? We'll use it twice. Here we go. There we go. And now, there we are, CBN. And what do I have to change? We don't need that cruft, right? 448. So each time we're referring to this, it is computing it. So is this call by need or call by name?
Name.
Call by name. Every time we see fn get v, what does it stand for? All it's standing for is this computation, print and return n of 4. So each time we see that, it goes off and performs that computation. That computation can have a side effect. You can do something like print out 4. Yeah. Put it increment a variable, yeah, in Scala, yeah. It's not only a functional language, but fundamentally, what this fn get v stands for is the computation. It stands for the expression, as it were, associated with this. And what's going on behind the scenes is conceptually exactly what we did above. We're passing a closure. It's a nicer syntax for it, eh? You don't need all these calls, eh? Comfortable with that? Okay. And that's call by name. Call by name is not call by need. It's a type of laziness, by name laziness. It's actually using that expression. Good or not? Good. And we saw that in Scala. It's very useful, right? Where do we see that? Where do we see call by name? Anyone remember? Yeah, so if we had array.fill, for example, we fill something of 10, and we fill a 10 length array, and we give it this as an argument, what are we going to see?
10 fours.
We're going to see 10 fours. Why is this printing out 10 fours?
That's the side effect.
It's evaluating that for each time. This is a call by name thing. It's taking in a recipe for how to compute each of these. Right? Huh? 10-4, big buddy. That may be lost to some people. CB radio. Okay, so last time we talked about the implications of this for language extension. This is a non-trivial issue because traditionally languages like Java, C family languages, traditional procedural, imperative, and object-oriented languages have had kind of this distinction between the keywords in the language, which have these magical abilities to handle non-strictness, and the code that you write, which is always strict. or at least you have to bend over backwards to enable non-strictness, like passing things in anonymous methods or anonymous classes, methods in anonymous classes, etc. So, ladies and gentlemen, just to make this very clear, imagine this case, we define a do-while construct to see how this call by name helps in language extension. Imagine a do-while construct here in Scala, and I'd welcome you to, if you want to type this in. This takes two by name quantities, a condition and a body, okay? And this is the definition of it. So do while means it unpacks to, you have the body up front, always, at least once, and then while the condition is true, you have the body again. Now, because these are by name, they're not evaluated until they're used. And each time they're used, they're evaluated again, right? Right? Each time, we just saw it, right? 10-4. Each time this needed to be used, for each of these 10 elements of the array, this was evaluated again. So each time we encounter body, it's evaluated again, and again, and again. Not just, this may look like one sort of occurrence of it, but no, we're going through a while loop, and each time it's hit, it's evaluating it again. All right? 10-4? Yeah. Okay. So here, we could actually create this, and then we can use it almost as if it's a construct of the language. I mean, after all, we could do something like do while n, some variable n is less than 10, print out something and increment n. That's how we increment. There's no, the x out is plus plus, and it's plus equals 1. Okay, so this is actually legal Scala. Here, this is legal Scala. Here you notice I, somewhat with malice aforethought, I divided it up into two parameter lists. The first one takes the condition, but this is a recipe for a condition. It's not a value. It's not saying right now, as soon as I call do while, is n less than 10. This is, because it's a by name, it's actually telling it, this is how you evaluate the condition when you need it. And so this tells it how to evaluate the condition, and this tells it the body. And you notice the body I specify in these curly brackets. After all, it's just an expression in Java. It's just a recipe for computing a value. And in Java, in Scala, and in Scala, it turns out we don't have to use, even though this is a parameter list, we don't have to put it in parentheses. Okay, we can just give it to it without parentheses around it. So this is legal Scala. And it would look to someone, if they came to this, they might think, oh, this is part of Scala, do while. It's a do while construct. I mean, we could put these in separate lines or whatever. It looks like a statement, doesn't it? A little bit? Well, that's what we can do with call by name, because this block of code is not evaluated immediately. It's not eagerly evaluated as soon as it sees it before we make the call to do while. This is not evaluated. Rather, this block of code is evaluated every time it's needed, and the condition is evaluated every time it's needed, and it allows us to implement this body. And indeed, this can allow us to implement control flow constructs, things that shape, under what conditions things happen very neatly. So legal Scala. To me, that's pretty neat. Someone of my generation might call it nifty. Someone of your generation, I guess, supposedly, I guess, you don't say cool anymore. You don't, I even heard for a while it was called sick, and then you don't say sick anymore. And now you say, I don't know, bad or something. I don't know. To me, though, that's pretty good. Nifty. Maybe it'll come back. Pretty much every of my habits seems to have become, it was very, very unpopular and gauche for a while, and then it became the fad. And people were going around with sweaters inside out and stuff like that, just like me, and then becoming non-fad again. And Still have my sweater inside out. Anyway, by name parameters. Whatever you call them, they're nifty. Okay? Lazy values. Let's talk about lazy values in Scala. Values are lazy by need, meaning that once they're computed, so we don't compute them immediately, but once they're computed, we remember their value. Okay? They're memoized following the initial evaluation. So here, let's go create this. Lazy val a equals println almost pi and 3.14159. Okay. Here we go. It's a lazy val. Notice it hasn't printed out almost pi. It hasn't printed that out yet. It's not because it isn't eating dinner. It hasn't computed it yet because we haven't used it. Now, if we say a plus a here, what do we expect to show up?
One print and double.
Yeah. So here we see almost pi, and if we do this more, we don't see the almost pi. Why is that? It computed it once by need. It waited to compute this until we actually needed it, and then it figured it out, and then it memoized, cached. It's more than caching because caches sound like something we don't have to maintain. It's not part of the semantics. We can throw away the value, recalculate if needed. No, it's actually part of the definition of the language that once it computes it, it remembers that value. Yeah.
So these are lazy defs versus lazy values?
Lazy
defs versus lazy values?
No, it's not so much. This is a lazy value. Where have you seen a lazy def?
The previous example.
No, I wouldn't say that's a lazy def. You talk about here, for example?
Yeah.
Well, these are the values. These are the recipes for the values. The def itself is not lazy. The def is evaluated as soon as we give it, but it's the values passed to it that are passed as recipes here. Yeah.
Could you pass in a lazy value for the body here, and then just have it?
Yep, and that's what we're doing here.
Oh, he means like the one we just created with pi.
Oh, for
Yeah, where it only evaluates it once.
so you're saying could we pass in what here?
A
For the
as
body.
the body.
Pass in A as the body. The body of what?
The body of the do while that you define.
Oh yeah. Oh, that's a pretty nifty idea.
Like in the definition of the do while as well.
Okay. Sure. Let's have B. Right?
Keep it as A. I want to see if it still doesn't.
Oh, you want to do it as A? Sure. Do while. So n is less than 10. We defined this var n before, so we still have that. And we'll pass in A as the body, like this.
Yeah, if that would work.
Sure. Okay. Value at did I not define? Well, fine. Okay. Var n equal. I thought I defined this, but that's fine. Okay. Fine. N plus equals 1, just to make it finish. Okay. Do what? Oh. Okay. I haven't. Sorry, folks. I have not. I forgot that I didn't define that. Let's go and copy it in here. Okay, there we go. And let's hope it doesn't have a fit. So paste. There we go. Come on. It's okay. Good. It was fitless. Great. And there we go. It's not doing it. Now let's define B. Okay. Here's B. Let's do that. And let's define that the same way. This is by need, so the first time it will be evaluated. We'll pass in B. What are we going to see?
One print.
One print. Almost pi. Boom. It's used 10 times. It's appearing 10 times, but the rest of the times it knows its value. Eh? Does that make sense? Okay. Okay, ladies and gentlemen, thank you for the questions. I welcome them, and that's great. Okay, lazy values. So these are memoized, following their initial computation. It remembers what this value is. Yes?
I just have one other question.
Sure.
About how does this lazy evaluation affects the garbage collection? Because if it's only, it evaluates it lazily and it says, I'm going to memoize this, when does it drop it? When does it say, I no longer need it?
After it's computed, it will drop it when, at the least, when it goes out of scope, when you no longer see that value as see the name as something that can be accessed. But with compilation, with optimization that comes with compilation, it may recognize that if you're not dealing with an interactive context like this read eval print loop, like this console we're using, if there's no other references, if there's no references elsewhere in the program beyond what's been seen, it may basically say it's not needed anymore because the name is not referred to anywhere else. So basically it's where the name can't be referred to or isn't referred to. And one way the name can't be referred to is this occurs in a method, for example, and you leave the method, and it's out of scope. You can't refer to the name, and therefore the name, if the name refers to something, that thing is no longer reachable via that name, and if it's the only reference to this thing, it can be garbage collected.
Only if it's purely functional, because you could just do something silly and return a pointer to that. And then what?
No, that's aliasing, and it's going to actually record how many things point to this. So that's part of what garbage collection does, and it's a quite sophisticated thing because you got to deal with circular structures where A points to B and B points to A. But people have thought long and hard about this, and they found algorithms which allow for accommodating circular structures and allow for safely cleaning it up, even in the presence of aliasing when multiple things can refer to it. Where you get into troubles in languages like C and C++, where you may not know there's a pointer because the pointer seems to be a double precision value, or it's a void star, and you don't know what it points to. And then it gets more hairy. But in languages like Scala, and in fact Java, it's well behaved enough you can do a lot better analysis. But Scala, it's even better than Java, and which is one of the reasons it can be great for parallelization. Okay, so by name parameters, lazy values. By name parameters, are these by name or by need? By name. Every time we refer to it, it recomputes it. This just stands for a computation. When it occurs, we recompute it. Lazy values, are these by need or by name? By need. Once it's computed, we memorize the value or remember the value when we use it. Streams, ladies and gentlemen. Streams represent potentially infinite sequences of values. Values that are available over time. They're kind of a incoming set of values. And streams are lazy. Values here are not evaluated until they are required by the computation. Streams, it turns out, are computed incrementally. And streams allow us to separate two very conceptually important but often entangled issues. They orthogonalize. They basically treat independently two issues. One is the ability to describe a computation, and the second is when to perform that computation. Okay? Streams are lazy. They support naming and defining an infinite computation, as we'll see, and then separate that from how much of that computation we want to perform. Okay? They're frugal in computing. We only compute if required, and they're incremental, meaning while you might have a stream that has a map following a filter, following another map, etc., each stage doesn't compute the results on the entire stream. Instead, each of those stages is performed incrementally. And what that means is that you won't be, in fact, performing multiple maps over this entire data structure. You'll be just successively manipulating values, checking if it matches this condition, adding this to it, mapping it to a double, etc. And this is going to be a huge impact in architectures like Spark or others, which are aimed at high amounts of data usage, because it allows us to use very limited memory, process each value as it comes in. There's parallel versions of streams and non-parallel versions of streams. And it turns out that definition of things in terms of streams can really simplify our ability to reuse abstractions. I won't be able to get to this today. We might hit it next time. But the idea is that actually we can reuse a lot more code if we can define things as streams. We get a certain amount of flexibility. And it turns out that they can be quite useful for domain-specific languages. Ladies and gentlemen, streams are a construct that go way back in time. And they reflect the reality that a lot of the ways we process things in the world, we're dealing with sets of data that are appearing over time in an incoming fashion, and we need to process them as they come in on an as-needed basis, for example. So streams are going to have this sort of conceptual simplicity to them that you'll see. It's hard to express how beautiful they are until you see them. And yet we're going to have this easy definition of kind of pipe and filter computation that we've seen before, where we have a pipeline of computations. Whether it's all on one line or separated in different portions of the program, it's going to allow us to specify very rich computations in an expressive fashion. And as we'll see, laziness in the form of by need is gonna play a big role. So I'd like to introduce streams, and I'm gonna introduce some syntax for them and some basic operations on them, and then we're gonna build some streams together. Okay? Okay. Suppose you want to get a stream. They sound good. How do I get one of them streams? I always get confused about that. 0 in the front. Let's try that. Yeah, here we go. Happiness. Okay, so here we have a stream. It composed of 3 pieces, 0, 1, and 2. Okay. Now this stream, you'll notice that it shows the stream here, and it shows the first of the elements of the stream. It actually hasn't evaluated these 2 elements yet. But we will see that we can do so very soon. We could do something like force here. And here we're going to have a stream, and it shows it all in detail, 0, 1, and 2. Okay? So here we're appending 0 to the front of a stream, and we've seen 2 ways we're building them up. One is via this, one is via that. And in general, there's a bunch of operators that allow us to build up streams that are finite length. And that's all fine and good. We can fill a stream with an expression, right, of finite length. So we could say, let's do import scala.util.random, I think it is, okay? And then we could say stream.fill 10, and we could do next double. There we go. And this is a stream of doubles. And notice that that stream of doubles, when we go to look at it, it has exactly 1 element shown. The rest of it is a question mark. The rest of it is not yet evaluated, ladies and gentlemen. Do you see that? Yeah. Warren?
Okay, so it's 2 things in a row. So first, if
Yeah.
say you have a stream of 10,000 numbers.
Yes.
And you want to access the 5,000.
Yes.
one,
Yes.
Does it have to calculate 1 to 5,000 feet?
Indeed.
5,000.
Indeed. Because in general, the later elements might depend on the earlier ones.
Yeah, so I was going to ask, like, if
Yeah.
that matters if it's
Yeah.
considered the penalty chart, but is there a way to get the 5,000 element without having to calculate the first 4,900?
I don't think so. I actually think you need to go through them one by one. I may be wrong about that, but I'm pretty sure that's the case.
Like, I mean, if there's a stream of the Fibonacci numbers, you obviously need to calculate the first.
We're going to be doing that in just a minute. Yeah,
Yeah,
exactly.
but if you like, it's
Indeed.
literally only
If it's
possible.
doubles, random doubles, well, even there's a dependency. But I understand what you're saying. Yeah, yeah. Okay, let's now though. These are ladies and gentlemen for finite streams, and we can have fun with them, right? Here are some doubles, and we can map them to be 2.0 times, whatever value is there, right? And here we get a value of random numbers that have been doubled, right? We can, given a stream, we can produce a new stream, okay? Map, filter, etc., right? We can filter out those that are greater than, so this greater than 0.5, for example, right? And we can force them, and we could see all of them then. But you'll notice that until we force them, only the first is really being processed right now. It's only doing as much work as it needs to get the first of them that matches this condition. So it may have generated several of them that didn't, and it's getting the first that does to get the stream out. Yes, is it truncated on the right? Is that it? Okay, so let's try this. Is this better? Like that? Is it truncated on the right?
About 4 columns less. There you go.
Okay. There.
Slide the screen over.
Okay. Okay. This way.
Yeah,
Keep going. Keep going.
there you go.
Keep going.
Okay. Keep going.
That's fine. Yeah.
Okay. 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 So, ladies and gentlemen, here it's gone as much as it needs to within this collection to find the first that's greater than 0.5, and then it stopped. This is a stream here, and it could be doing this for 10, or it could be doing it for 100, and the rest aren't yet computed. Let's be very clear about that. The rest aren't yet computed. It's actually not performed this for most of this 100. It's only performed enough of these next doubles to get the first of them, which matches this condition. Okay. So we'll continue to look at this. Okay. Now let's have some fun. This is where it gets fun. Let's create infinite streams that are unbounded. Okay.
Before you go there,
Yes.
if it hasn't performed that, has it actually come up with those 10 doubles or not even that?
No.
Okay.
No. It's only performed enough of them as it needs to get the first that's greater than 0.5. The others are not yet evaluated. It actually hasn't performed the operation needed to compute them, this next double. Okay? Okay, ladies and gentlemen, let's do stream continually here. This is kind of the most kind of simple. Stream continually. Next double. Well, we could have fun. Okay, let's do 3.14159. Okay? Here's a stream of things that are almost pi. But that's not particularly interesting. We could have a stream of ones. That's kind of a little bit pleasing. And, maybe now we want to perform a stream that will do, we'll actually add the ones. Okay, I've got to be careful here. I think this takes 2 arguments. Yeah. Okay, here's the stream of things that took the ones, and then basically starting at 0, it's adding up sets of them. So I'll take the first 10 of them, and I will force it and go see them. So here we have a stream of 1, 2, 3, 4, 5, 6. It's basically accumulations of these ones. We'll come to that again in a minute. So I could take a stream and basically perform processes, but this is an infinite stream of ones. Or if you want, folks, an infinite stream of next doubles. This is a stream of double precision values generated randomly between 0 and 1. How long is it? It's unbounded in its length. However many you need, it'll give them to you. Yeah.
Can you reduce it?
You cannot add them all up, but you could reduce sets of it, and that's in fact exactly what I was doing. I was summing them up successively here. So I could do a similar thing here. I could do continuously next double and take the first 10 of them. Okay. Okay. So why is this not a happy camper? So let's take D and add D to D, and it probably will need type information. Yeah, fine. Sometimes it is a bit of a pain. Okay, double. Okay, so it requires any val to any val. Mumble. Why is that? Okay.
Using scan.
Sorry.
He says you're still using scan, and scan doesn't work like that.
Yeah, it should actually allow us to. Oh, sorry. It needs to take 2 doubles. What am I doing? That's why I'm screwed up. So this should be this should be D1 and D2. D2 double, and we'll add D1 to D2. That's what it is. Okay, and still unhappy. It found a double to double. It should take this. Okay, I'm not sure why it's not getting the requisite. Oh, no, 0.0. That's why. Mumble. It was saying this is an int, and you're not giving me something consistent with the ints. The only thing that matches both int and double are things that are any vals and mumble. So this is, ladies and gentlemen, successive sums of those numbers, of these random numbers for the first 10. Yeah.
What's the scan and zero doing that?
This is, so scan needs some starting, so basically this is saying successive values should be added to this thing, but it needs a starting value to have at first to start adding. And so basically this is going to allow it to start, the 0 is going to allow it to start with the actual number. If I made this 100, watch this, if I made it 100, it'll be now offsetting the entire thing by 100
But whenever
here.
you scan with 0,
See,
the first element is always 0.
100, sorry?
All of your scans that are 0 start with the number 0.
Yeah, this is in fact the starting one as well. So it's starting here with 100, and then it's adding that 100 to the first double, to the second double in that list, etc. Yeah. And so if I don't want that double, what I could do is I could drop the first one, I could drop the first one, and then I could take the next 10 and force it, and basically I'd see the successive ones, and I could start from 0. So essentially what it's doing is it provides a kind of the base value to use when adding things up. It is the first of those items, and it's going to add the next one to that, and the next one to that, etc. Okay. So this is continually, but let's have more fun. Stream dot from 1.
Doesn't seem like a location.
Okay, watch this. Force 10 and, force 10. What am I doing? Take 10, force. 1, 2, 3, 4. Okay? Or I could do this by 2s. Now it's going up by 1, 3, 7s. So what is this from 1 creating?
Start with.
Yeah, it's basically all whole numbers. 1, 2, 3, 4, 5. It's an infinite stream, ladies and gentlemen. We can go as long as we want, right? I mean, we did the first 10 there. We could do the first 30, right? It's an unbounded stream of integers. This is an unbounded stream here of the odd integers. Got or not? Okay. So this is an unbounded stream of the odd integers. Okay? And in general, we could do stream iterate, which will take a starting value, which is always the first, a little bit like scan, and a function f, and it will apply this function repeatedly. So maybe this function adds, in the most trivial case, to duplicate functionality we've already seen, maybe this function adds 1 to whatever it gets in. So if you give it, you know, it adds 1 to it. So if the starting value be 1, and the function adds 1 to it, the next one will be 2, the next one will be 3, 1 plus 1 plus 1, etc. So iteration provides a way of successively iterating this function. But the function could double things, right? So let's do stream iterate. This is going to be fun. Stream.iterate. And we'll start with 1. And how do I describe a function which doubles the existing value? Well, there, right? Okay, so this is a stream. The first element is 1. Remember, the first element is the start value. Okay, what will the second element be?
2.
The next? Oop.
4.
Good. So let's take 10 of them, force it. There it is. Numbers you should all know and love. Right. So, successive numbers, we didn't print them. 1024, 2048, 4196, 8192, etc. Those are all there as potential numbers, and if we need them, they're there for our taking, right? If we don't need them, they won't be computed. Here, we've taken this function, and we've taken the first thing we wanted, that's the first element. The second one is that function applied to the first element. The third one is that function applied twice to that first element. Next one is that function applied 3 times, just like what we see here, right? The next one will be f of f of f of start, etc. So
here it's not memoizing the previous one to multiply it by 2, or?
it actually is.
Okay.
It's yeah, I'm pretty sure that's the case. So how would we check it? It's actually, we could do here. You want to see if it's memoizing? Yeah, let's see. So we'll take an n, and we will here. We'll take an n. It's an int, and we will go and print n. Print n, print ln of n, and then we will return n times 2. Okay. 1, 2, 4, 8, 16. So this is just taking the previous value, and then it's going to be applying the function to it. So it's not going back, having to go back each time to 1, 1, 1, 1, 1 to reapply that thing each time. It's using the previous one and then applying the function to that. Okay? Okay. Fun. Okay, so let's define perfect squares here. So let's import Scala.math. Let's import all the things in Scala.math, and that's going to give us some things we'll want to use here. Okay, Vals squares. We'll give 2 options for squares. Okay, one of them is going to be a lot more efficient than the other. Stream.from1. Okay, and how could we get the squares here? How could we get squares of successive positive whole numbers? What could we do?
Map them to squares.
We could map it. Let's map it. You could say, well, how are we going to perform a map over an infinite thing? A map requires a scan, sort of successively going through each element, and that will never compute. That will never terminate. It's going to be an infinite, unbounded sequence of integers. That's not the case, ladies and gentlemen. In streams, these things are performed incrementally. Map is only going to do its map for as much as it needs. Okay, so let's here take map of each integer, and let's square it, right? Here we are, okay? And let's take the first 10 of them, and let's force those. There we are. Ladies and gentlemen, these are the squares. These are the squares. These are the squares of whole numbers. How many are them? They're unbounded in length. How many do you want? That's the question. How many of them do you want? How if we want to get those that are greater than a certain thing? How if we want to, let's get all the squares between 10,000 and 15,000. What do you think? Right? How would I do that?
Filter.
Sorry? Filter. Okay, good. What do I write?
Take in a number.
Okay, take in a number. And remember, filter requires a predicate, so we give it a function. And that function needs to return what?
Boolean.
It's a Boolean, yeah. It returns true or false, okay? So return a Boolean, and one condition will be it's greater than or equal to 10,000, and I is less than or equal to 15,000, right? Let's take, well, let's force them. Yeah, okay. What is it doing?
Running all the squares.
Yeah, okay. Oh my gosh. But what's going to go on? It's going to go on here. Why is it going on? I didn't take.
Oh, it's going to keep checking the ones over.
It's going to keep on checking. It doesn't know. I mean, it doesn't know. Like this, maybe the square of 1,000,000 is between this. Okay, so Control C here. Kill. Okay, back into Scala. Message. You should be a little bit careful with infinite streams in terms of what you ask them to do. Some things that might be obvious to you are not going to be so obvious. So what can we do here to remedy that? Let's take the first 10 of them. What do you think? Are we sure there are 10? first 5 of them, and force those. Okay. Okay.
There might not be 5. There's 5.
There's 5 of them. 10,000, 10,021, 10,0404, 10. Okay. Do we feel lucky?
Lots of space. Run that again. I want to see if it runs faster on the second time.
Sure. It's actually okay. So let's do it.
No, it does not.
Okay. Now, why doesn't it run faster?
Because they're still writing.
Because, well, we're still computing it from the start. If we had done squares, val squares, and we had done this, copy. There we go. And now if we said, so there are squares. If we now did squares dot filter, and I don't want to retype it, so I'll go do this again. Here we go. Boom, boom. Okay. Okay. Yeah, it's still not clear if it's faster. It basically is going to compute. Let's go take a look at squares here. What's going on?
They all exist now because you used them.
They all exist because we computed them. Let's be clear. What would they have looked like? Squares.
They would have said
I'm going to say squares B. Okay. What would it look like right now if I did this?
1.
Only one of them. How if I do squares B dot take the first 10? Now if I do squares B, what do I get to see?
Still 1.
Okay.
There's just only 10 long.
Yeah, but what would I need to do here? Force. Now what do I do if I take a look at them? That's the first 10. It's computed them, ladies and gentlemen. Just taking the first 10 didn't force it, because taking them yields a stream, and that's still not evaluated. By forcing them, then they're all computed. Or, okay, let's go to square C. Square C here. There we are. What else would cause them to all be materialized, to be computed?
You try printing numbers?
Yeah, I could try printing them, but watch this. Square C dot filter, right? Do I still have it in my paste buffer?
It'll reveal them up to the one that hits the first filter.
Yeah, it'll revert them up to the one that meets the first filter here. So here, square C, all these have been computed because they needed to be computed in order to find the first 10
That fit.
that match this condition. Nifty or not?
Somewhat nifty.
You ain't seen nothing yet. Okay. Okay. Okay, so here's some more operations on stream slips. You kind of seem to come out by dribs and drabs. You can add item to the front of the stream. Should have shown this at first. You can find the head of a stream, the first one, s.head. You can find the tail. How is s.head different from s.tail? What does s.head reveal? It's the item. In this case, it might be an int, for example. S.tail is a what?
Everything but the first.
Yeah, it's everything but the first, so that's a stream. That's a stream. S.take, what does that return? Stream. That's a stream, ladies and gentlemen. It itself gets a stream of the first n. We may have an infinite stream S, and we take the first 10 of it, and that's a stream. It's a finite stream now. It's a stream of like 10, but it's still a stream. S drop n, this drops the first n, and S tail is like S drop of 1. S dot empty S is the stream empty. Have a finite length stream and it runs out. Here we applied a reducing function to successive prefixes, and there was some initial value, which was the first value, and then we successively applied this reducing function where we added things together. We could force evaluation of the stream, force it to materialize. Now, S dot distinct, used with caution. This is looking for all distinct elements in the stream. Why do I say used with caution?
I think if you use on infinite stream, then okay.
Yeah, if you use it on an infinite stream.
Oh, actually, that's another question. Is there some sort of way that you can use like a Boolean to determine if the stream is infinite or not?
I think you'd have to solve the halting
Okay.
problem to do that. Yeah, it's a good question. Alan Turing asked it earlier.
So, like, I don't know if there was.
But would it be a
if
type
stream
thing?
infinite, then it would have some sort of value that you can look at, but,
Yeah.
Because like once we take 10, we know it's finite, so there would be nice if there was a Boolean that says isn't infinite.
Is it known to be finite is another question. You could have a thing, is it known to be finite, but maybe it is finite and you don't know it because you have a criteria that it's not.
I guess you could
Yeah.
fold into a class really easily or something if you really wanted.
Interesting stuff. Sliding window. We could create sliding windows that each of which produces a stream. Map, filter, reduce, etc. Okay, we've seen some of these things. Okay, let's do the Fibonacci's. Fibonacci sequences, ladies and gentlemen. Def Fibonacci. This is going to examine sort of a co-recursion. We're going to be producing the stream while maintaining state here.
Can we just do it in one value defined as opposed to a function?
Do it in a value?
Yeah, like isn't it just you type the right things in when you make a stream and you make a stream?
Yeah, we actually could do it, but So yes, I'd like to do it with this because it'll be important for something on your assignment. Okay. Okay. Fibonacci. We're going to take in some things here. Okay. We're going to take in an A, which is going to be an integer. Yeah. Let's make it a long. A B, which is going to be a long. And this is going to give us a stream of longs, okay? How are we going to define this? Does anyone remember what the Fibonacci sequence is?
1, 1, 3, 5, 8.
Okay, I mean, you could include 0 in there, but 1, 1.
And then,
Is it 3?
2, 2, 3, 5, 8.
2. Where did the 2 come from?
1, 1.
yeah, so
1 plus 1. The next one? 3 is 1 plus 2. The next one is 5. That's 2 plus 3. So every one is the sum of the 2 before it, right?
F of n equals F of n minus 1, F of n
Yeah,
minus
good, good. Okay, so how could we define that here? Well, what's going to be the head of it? I'm going to use A to indicate the one 2 earlier, and B to indicate the one, or sort of successive one. So A and B are successive. So I'm going to have A added to a stream that consists of B. So those are going to be the first 2 elements. And then what's going to come next? That's the key question. What's going to come next?
Fibonacci.
Okay, good. Fibonacci of what? What is in this? What are the arguments to Fibonacci?
B plus A.
B and B plus A, or A plus B. Oop. Okay, recursive. Okay, it needs a result type. Yeah, fine. So what is this going to return? Stream of long. You notice there's times Scala needs result type. In here we're telling it to depend on it. It's not quite. It would actually have to be fairly sophisticated to realize, okay, whatever the return type is this, it has to be return type to the entire thing. So yeah, this is Fibonacci. Okay, so ladies and gentlemen, Fibonacci. How do I look at the first 10 Fibonaccis?
Take 10 force.
Take 10. Let's take a look at Fibonacci. But Fibonacci. Sorry. Yeah. So let's do val Fibonacci's equals Fibonacci of 1, 1. Okay? There we go. There's a stream. Now Fibonacci, we'll take Fibonacci of the Fibonacci's. We'll take the first 10 of them, and we'll force them, right? There we are. 1, 1, 2, 3. Okay.
3 1s.
What?
That's your definition. You shouldn't have the B in the definition.
Okay. No, I disagree. But okay, so that's an interesting thing. What's wrong here?
B, B, B again.
You're adding too many things to the stream.
You've got A, B, B, A
You're
plus
adding
B.
A and B, and then you're
Oh, you're adding A and B, and then you're absolutely right. What we don't want is what we don't want is the B, right? There we go. Okay, yeah. There we go. Okay, thank you.
It would be nice if the Fibonacci's value just updated when you change the function.
Yeah. Okay, so there we go. 1, 1, 2, 3, 5, etc. Right? So what's going on here? This is the first element. The next element will be what? Well, we're calling Fibonacci of this, so the next element will be B. And then that's going to be called in turn, and the next element is going to be that A plus B. So that's going to be going, and et cetera. So here are the Fibonacci's, ladies and gentlemen. There are the Fibonacci's. And how many do you want? 100 of them? Now, the Fibonacci's, having been computed up to 100, there they are. If we want more, it will compute them on demand. On demand. As we need them, it'll compute them. Okay, now, we could further ask which of these Fibonacci's are, for example, prime numbers. Okay, so let's go put in place or square numbers, excuse me, our squares. So I'm going to define an is square, def is square here. Okay, and this will be is square of a long. It's going to test if a long is square. And here we're going to say there's different ways we could do this, but I'm going to just check. We're going to say the sort of the rounded root of this is floor here, floor of square root of n. Oh, I've got to import Scala math because my Scala session died, so we'll do that. And then we'll test if root times root is equal to n here. Okay, boom. Okay, so import Scala dot math dot boom. Okay, there we are, and there we are. There's is square. Here we take the round of the floor of the square root. So we're taking the square root of n, basically, and we're rounding it downwards. Okay, round and floor are both needed here for type reasons. And then we're going to test if whatever we get out of that times itself is directly equal to n. In other words, is it a perfect square? Okay? And now we could take the Fibonacci's and we could, how would we find the first 5 squares of the perfect squares? Or the first, say the first 2.
Use a filter that uses that.
Filter is square of, you notice is square returns a Boolean here. We're testing there. Is square of what? Whatever it is, right? Okay. Okay, so that's a stream of Fibonacci's that are perfect squares. So val square fibs, right? Square fibs dot take of, how lucky do I feel? First 3, 144. First 4.
And we wait.
Be a long time, folks. Be a long time. So these are the first 3 instances of the Fibonacci's that are perfect squares. And if we waited long enough, we might find another. Is this an infinite stream?
Yes.
Square fibs is, yes.
Quite possibly. I'll leave it to those who engage in number theory to tell me if it indeed is infinite or not. Okay, we'll finish it with that. Time is up. We will be continuing on streams, and we're going to see next time why they allow us to compute things incrementally. Okay?